So solutions to these problems on transformation matrices and coordinate frames. Let's just get right into it. So to begin with, we're just building single matrices to do specific transformations. So in this first one here, we want a matrix that will translate the coordinate frame by 3 minus 6, 2. So that's as simple as saying the matrix that we need will be an identity matrix in the base, like so, and then we have the numbers 3 minus 6, is it not? 3 minus 6, 2. So that would be the matrix to translate that. And just to set it up here, we'll look at, so I have an Excel sheet here where we can fill in these things. So if we just say we're going to imagine that we just start with an identity matrix, and then I'm going to add translation by 3 minus 6, 2. And so I can just say, right, 3 minus 6, 2, and we'll end up with this. We don't need this until in the last, or in the second problem, when we're going to take a few of those transformations and add them up. So let's stick to one node for now. So B, triple the scale of the coordinate frame. So we're going to triple the entire scale, triple the length of all the coordinate frames vectors. And so that should look like this. We have a matrix here, and we're not going to change its point of origin, which means that this column is the same. The other 3 columns are all vectors, so there's a 0 here, and then we're going to triple it. So there's 3 here, 3 here, and 3 here. So here we have the vector 3, 0, 0, 0. Here we have the vector 0, 3, 0. And here we have the vector 0, 0, 3. So we've simply taken the unit vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1 and tripled their length. So this is the matrix that will, it's a scale by 3, 3, 3. All right. So finally, a matrix that doubles the coordinate frame's z-axis and halves its y-axis. So whatever the coordinate frame before is, we want to make a matrix that, if added to it, will double the coordinate frame's z-axis and halve its y-axis. So we'll build a matrix that looks like this. So the x-axis is supposed to be unchanged. So 1, 0, 0, 0. We're supposed to have 0.5 its y-axis. So we take the y vector and halve the length of that, and that multiplied with the current coordinate frame, whatever it is, will have its y-axis, and then we want to double its z-axis. That was what was asked for, right? Double the z-axis and have its y-axis. And we're not changing the point of origin. So this is again a scale. This is a scale by 1, 0.52. Okay, so now we want to rotate the coordinate frame 30 degrees clockwise about the z-axis. So a rotation about the z-axis, let's just set that up here. First, what we're going to do is we're going to take the angle So we'll just say C here equals the cosine of 30 degrees, because that's what we're working with, and S equals the sine of 30 degrees. And then the matrix that we build, 30 degrees clockwise about the z-axis. So rotating about the z-axis, we'll leave the z-axis unchanged since we're rotating around that, and it won't be affected by the z-axis here. So we have cosine minus sine, sine cosine. That would be a counterclockwise rotation. So actually we'd say C is the cosine of minus 30 degrees since we're going clockwise. But when we're using this in a program, you just figure out which is which by trying. So it'll look like this. Take the cosine and the sine of the angle. In this case, since we're rotating that direction, we simply change the angle to minus 30 degrees. That's the only difference. Otherwise, we could actually take this minus here and put it on the other side. So the cosine of plus and minus 30 degrees is the same. It's only the sinus that changes. We could simply take the minus from here and put it to here in order to rotate clockwise, but no matter. This is the matrix we make. And if we go here into Excel, let's just update this matrix again. And let's just say this equals cosine of minus 30 degrees. Is cosine not a function here? Cos, yes, it's a function. Returns the cosine of an angle. And say that for minus 30 degrees. Right. The cosine of minus 30 degrees is not 0. Equals sine of minus 30 degrees. I wonder if this is in radians. So we should do minus 30 times pi divided by 180. Alright, what's going on here is simply the fact that the cosine of minus 30 degrees here I put into this, but it's not wide enough here, the spaces. So if we say minus sine of minus 30 degrees, it says minus 1, but if we just make this a bit wider, we'll get the correct number. I'm still feeling that we should change this to radians. 0.1415 by 180. Yes, that looks more like it. Times 3.15 180. I can just take what we have here, just stick it in here. Except we're going to put plus on that. And finally we can take this, simply copy it in here. Okay, so this would be the correct numbers for this. No big deal though. as long as you understand how this is built up and calculate this cosine, then those are the numbers that we'll end up with here. Alright, so final part here, rotates the coordinate frame 135 degrees about the y-axis. So then we simply have to remember what the rotation around the y-axis looks like. So again, we'll just say C equals cosine of 135 degrees. S equals the sine of 135 degrees. And then the matrix we build will look like this. So we're going to leave the y-axis unchanged. And then we have cos here, sine here, minus sine here, cos here, and the rest is the identity matrix. So there, this is what it'll look like. And if we set it up in Excel here again, let's just see, first transformed by C, then by A, and finally by E. Let's just go into the E matrix here, no, third matrix here, and set this up. So this should equal cosine of 135 degrees times pi divided by 180. Okay, so we put the cosine here, the cosine here as well, and we put the sine here, 135 degrees times 3.15 180, or you can simply switch your calculator between degrees and radians to get this right. Minus here. Okay, so now we've got the numbers right. So these would be the numbers. You can see 135 degrees is giving us the same sine and cosine. That's simply because 135 degrees is 90 degrees plus 45 degrees. So we're going up to 90 degrees, which is vertical, and then back down to 45 degrees, except we're getting a minus on the cosine and a plus on the sine. Alright, so this would be the numbers in this matrix, the matrix in part E. So if we run through this here, the first one is a translation, the second one is a scale by 3, 3, and 3, third one is a scale by 1, then 1/2 for the y-axis and 2 for the z-axis. And we have a rotation around the z-axis, clockwise, making it the minus. Then we have a rotation around the y-axis by 135 degrees. Okay, so now to do the second part here, let's consider a coordinate frame that is first transformed by C from the previous example, which is double the coordinates frame z-axis and have its y-axis. Let's go in here and say, let's first do that, which is, this will be 1, 0, 0, 0, 0.5 here, 0, 0.5, like that, to get the numbers in there, and 2 here. Okay, so first, to make all of this just a little bit wider so that the numbers display correctly. Alright, so here we have these matrices. So this is the resulting matrix, and the way I set this up here is that here we're calculating, doing a matrix multiplication. So we can just see that for this, the cell at the first column, second row, we're taking the second row and the first column here, and we're taking a dot product between them, and that's what ends up here. So this times this plus this times this plus this times this plus this times this. Dot product between this row vector and this column vector is what ends up here. Same for this spot here. You can see that it's in the second row, third column, so it's a dot product between the second row and the third column of the matrices. If you set that up that way, then this matrix here simply takes the numbers from the previous matrix. So now we've transformed with this matrix, which is now scale by 1, 0.5, 2. Okay, then by A, which is translates the coordinate frame by 3 minus 6, 2. So translation by 3 minus 6, 2. Let me simply put 3 minus 6, 2 here. Let's make this a little bit wider as well, to make sure everything's legible. Okay, and then the resulting matrix is this. And you can see that since we're translating after we've scaled, the resulting translations aren't the same as the ones we have here. The Z translation is double, and the Y translation is halved. If we'd have done it the other way around, translated first and then scaled, the translation would be the same. So then we'd end up with these things scaled, just like they are here. But this would be the unchanged translation, since the translation would have happened before we scaled the vectors that we're using to translate. Okay, so this is this final matrix here, and we already put this in here, which was a rotation about y-axis by 135 degrees. Okay, so rotation around the y-axis by this, and when that's added to it, rotating this whole thing, we still have the same point of origin. That doesn't change, we're rotating it around itself, but this rotation happens here. So this is the resulting matrix. If we make it a little bit wider, we can see that these numbers are, okay, can be a little bit more exact like that. So, alright, fair enough. And so we have done A now, build the coordinate frames matrix. So what we do is simply we do a matrix multiplication, basically build the first matrix. We don't really need to do a matrix multiplication here, we just end up with that matrix. Then we take the matrix that we have and multiply to the right of it the next matrix. So first one is the scale, then is the translation, and we get the resulting matrix here through a matrix multiplication. And then we take the resulting matrix from that and do a matrix multiplication here, where on the right side of that we add the rotation. So this is the resulting matrix. This is the answer we have here. And now show the coordinate frames vectors and point of origin. And to do this, we simply have to read from the matrix. So let's look at what the matrix looks like here. Okay, so we can write this up 707, we have there. So this matrix looks like this, minus 7, no, 0. Let's just make it short. Minus 0.7, 0 here, and we had 0.7 here as well. Then we have minus 1.4, minus 1.4 here, minus 1.4 here, we had 0.5 here, 0 and 0 here. And then we have 3, minus 3, 4. 3, minus 3, and 4, and 1. So this is the matrix, and then we simply say this is the A vector, or the modified x-axis. This is the B vector, or the modified y-axis, and this is the C vector, or the modified z-axis, and this is the point of origin. So if we were to draw this vector, and this vector, all originating from this point, that would look like the coordinate frame that we're working with at this point. Okay, so now we've shown the coordinates frames vectors. Basically, we can say these vectors are, oh no, never mind. Let's set this up here now. We can also say, if we set up a matrix multiplication here, so this times this equals, and here we say this equals this times this plus this times this, this plus this times this. So here we have times this plus this times this plus this times this. Here we have this times this plus this times this plus this times this plus this times this. And finally we have this times this times this plus this times this. Okay, so understand. So okay, so this is the resulting vector. So now we can actually say, if we take the numbers from here, just do it this way, like so. So take the formatting. Okay, so now I've simply taken these numbers here. Let's make this a little bit wider, all of it, so we can see it better, and make everything else a little bit tighter. Okay, so here we can say that if we multiply this with the point 0, 0, 0, 1 here means it's a point, we get the point of origin. If we multiply this by the vector 0, 1, 0, we get the y-axis, or the b vector, the modified y-axis. If we say this is the vector that we're going to multiply with, this is the x-axis. And finally, if we make this vector here, basically the z vector or the j vector, this is the axis that we get up, the c vector or the modified z-axis. Okay, so now that we've set up this matrix multiplication here, where we've used it to transform the base unit vectors and the point of origin here to find these numbers, find these vectors and points here in order to answer this question, we can now easily answer question C and D here, which is basically this point is drawn into the transformed coordinate frame. What are that same point's coordinates in the base coordinate system? And all we need to do in order to do that, since we've already set up the matrix here, we have this matrix, all we need to do is say if there's a point 4, 8, minus 2, 4, 8, minus 2, we simply do a matrix multiplication on that point. So in the end, this is the dot product between this row and the column point here, which is the homogeneous coordinates 4, 8, minus 2, and 1, because it's a point. So this is the answer. This point in the local coordinates drawn into this coordinate frame have these coordinates. That same point has these coordinates in the global scope. So inside our shader, when we do our lighting calculations in the global coordinates, if we're going to work it like that, we'd say this is the point that we actually send in a vertex buffer, part of our model. But after being transformed by this, these are the coordinates that we actually use to do all the calculations, because our lights and our camera and all that are set in the global coordinates. So we need to get these in global coordinates to work along with that. So this is the point, and this is what we get. This is the answer. And finally, the vector 4, 8, minus 2 is defined in the transformed coordinate frame. What are the same vectors coordinates in the base coordinate system or in the global coordinate system? And the answer to that is now this. So we get something different simply because the point of origin doesn't affect it. Now it's a vector being transformed, so only this part has an effect. Now it's a point being transformed, and it gets the same coordinates, except we add to that the point of origin. So a point starts at the point of origin, and it matters where it starts from. A vector only has a size and a direction, so it doesn't matter what the point of origin is. So this is the point, and this is the vector. So that's it for these setting up transformation matrices and coordinate frames, setting them up as matrix multiplications, the combined transformations, and then transforming our points and vectors using the matrix built from the coordinate frame that we're trying to set up in our three-dimensional space.